Okay, I'll just wait for one more minute since there's a lot of people still joining. Can everybody hear me all right? Great.
Yep.
Okay, well, let's get started. So this is a bit of a change in schedule to what we originally planned, but this is a little bit more useful, I guess, for everybody here, especially with regards to homework 5. So this week is data visualization week, which is kind of exciting for me because this is my main research area. And usually I do some like theory of data visualization first, like how do we create data visualizations like conceptually, what are like some guidelines, some rules, what are good visualizations for different data types and scenarios. I wanted to start with that, but I think it's more important to get you like an idea of like how you can actually implement visualizations first so that you can use those skills for your homework. So we'll start with this today, and then we will do the theory and like the design guidelines and so on Thursday. So today is code, and Thursday is mostly going to be slides and some discussion about visualizations. So the thing is, data visualization with Python is a bit of a mess. So in R, for example, you have essentially 2 libraries, ggplot and base graphics, and that's it. In Python, you have hundreds of libraries. And just to name a couple of the ones that are very popular: Matplotlib, Pandas visualization, Seaborn. Then there's a ggplot version for Python. And these are kind of like the one that build on Matplotlib. So Matplotlib is kind of like the elephant in the room that everybody is kind of like building on top of. But these kind of like have been kind of like, there's now additional visualization tools that are compatible with Python, but not necessarily with just Python, but with these notebooks environments. And they kind of require a web browser. And among them is Plotly, Altair, PDVega, and Poke. So there's more. I linked to some blog posts to discuss different pros and cons. Although I think there is now essentially 3 libraries that stand out. Matplotlib is kind of like the thing that you have to know a little bit, at least, so that you can understand what other people are doing. Seaborn is a great library to do some more complex charts with a single line. And Altair is kind of like the best of the web-based tools. Though Plotly is pretty cool too, but it gets a little bit more complex. I like Altair, and so we'll cover those 3 today. You will not be an expert in any of those 3 after this, but you should get a sense of what is possible with each of these libraries. How do you approach it conceptually, and then you can find the documentation and then look at like where you can take it with these. Generally speaking, there's 2 different approaches to data visualization. There is plotting libraries and drawing libraries. And for example, in Seaborn, you can say violin plot. It's not exactly called like that, but that will create a violin plot, will do the whole data aggregation for you, and so on. Whereas in Altair, it's more about like, here I have a mark that I'm moving, that I'm mapping to a point, and then I'm moving that around. So it's more fundamental drawing. And I hope you'll get a sense for this difference between the 2 of them. And then finally, just a note that all of these libraries here are somewhat limited in terms of their expressivity. So if you want to do some super custom thing, like for example, a genome browser or some like complicated network visualization, these are not the right tools. Then you have to kind of like still get your hands dirty and do something more complex with a language such as D3 and JavaScript, which is kind of way beyond what we cover in this class, or even WebGL, like if you want to visualize MRI scans or something like that. I teach like D3, for example, in my graduate data visualization class. So if you're super excited about creating custom visualizations, that could be a course that you could take. Okay, so let's get started. Matplotlib, as I said, is kind of the most important library out there because it's just like so it is pretty sophisticated and it is widely used, and we will be using it a lot in examples. And it is also the basis for all of these other libraries. Okay, so how does Matplotlib work? We've already used it a little bit, so I'm kind of repeating things a little bit. So one thing that we might not have explicitly said, if you use like a code like this where you have a %, this is not standard Python, but this is something that is IPython specific. And that in this case here, this tells that I want to see all of these visualizations inline directly in my notebook instead of like saving them as files. Then here I'm creating my very first Matplotlib plot. I'm creating like a Fibonacci series, or I'm just like defining it, and then I do PLD plot. And so here, this is my first plot, and plot is just a line chart in this case. So simple enough. The plot command uses a figure object to plot in. And if you haven't defined a figure explicitly, it will automatically create one. If there is already a figure, it will plot to the latest figure. And sometimes it makes sense to create a figure manually. So here is how we create a figure, plt.figure, and then I give this figure here a size, and you can see that this doesn't do anything by itself. And this figure, we can then add subfigures or subplots to it. Let's do this here. Again, just to show this line, again, we simply say fig dot add subplot. And then here I'm saying create a figure with only one by one, with a 1x1 grid, so only a single figure in it, and return the first figure. These are the three parameters here. And then I'm doing the same thing again. So this is kind of like a long-winded way of doing this here. Doesn't make much sense if all you want to do is plot this single chart, but you'll see that this is useful in practice. Then we want to do things like add titles. So here's a super title. I call this my line chart, and then I'm setting an X label and the Y label with my sequence and my values. And you can style that in different ways. You can say font size and bold and so on. So again, nothing particularly exciting or surprising. It kind of gets more interesting when we want to plot multiple times on the same axis. This is something we often want to do with line charts. And so what I'm doing here is I'm taking the Fibonacci series and plot it. Then I'm inverting the same Fibonacci series. And then I'm doing like a horizontal line, like at level 10, just like a straight line. And the way I'm doing this here is like, first I create my figure, then I add a subplot, a single subplot that I store in this variable here. And then I'm calling this again and again and again. And so this does the plotting. So let's run this and let's look at what this does. So you can see like these couple of lines here, they create these three lines and the chart around it. And so this is kind of like what you would expect. My Fibonacci series going down, Fibonacci series going up, and the horizontal line. The color here is picked automatically. But I also like wanted to create a legend, and I can do that by calling the legend command. And here I'm doing something a little bit like these lines. Each of these lines is kind of like it's called like an artist or yeah, it's kind of a weird terminology. And I am like the plot command returns this. It actually returns a list of those elements. And so I just want the first one. And so I'm doing this like weird thing with the comma here. So this is just like giving me the first one using tuple unpacking. And so now I can do, I can actually use another tuple. Here are my different kind of lines. And this is what I want to call them. And so this is the way I could label, like I create these labels: Fibonacci rising, Fibonacci falling, and constant values. Alternatively, we can also like, this is kind of like the best way to do it, just calling my plot a couple of times. But you could also do this here, where I simply like specify them in sequence. So the interesting code bit here is this. So you can see I have my Fibonacci series, my inverted Fibonacci series, and my just straight line. But if I do it with this, like all in this one call, the plot function does expect X, Y for each line chart. So in these cases here, it just assumed that your kind of like X is a sequence. But if you want to specify multiple series at the same time, you have to explicitly specify your X and Y. And so I'm just like doing this with the range here. And so this will create the same chart as you saw before. It just does it like in a single line, in a single plotting line here. And in this case, you can see that it returns all of these three lines into, and I'm using tuple unpacking to assign it. And then I'm using this again to label it down here. And by the way, don't worry, like this is, this looks complicated, but it's all just like simple options, right? And you're not supposed to like know this by heart now. You can just always look it up and just refer to this notebook or to the documentation when you want to visualize something. Okay, so now we have done multiple lines, multiple charts basically in one single figure. Now we want to look at how can we create multiple subplots. And so here is where this like gets a little bit more interesting. We want to create a subplot in a grid of 2 by 2. Let's take a look at what we're creating here. I'm creating like a straight line up, the Fibonacci series, and then this dashed line with kind of like some specified values. Okay, so what I'm doing is I'm simply saying, like, I create the figure here, and then I'm adding a subplot. A subplot in a grid of 2 by 2. This is like the element 1. And then I'm storing this subplot in my subfig 1 here. 2 by 2 element 2, 2 by 2 element 3. And those are the 3 figures later. And then I can kind of do something like I can refer to these explicitly and plot it. So here, subfigure 1, I'm plotting range from 0 to 10, which is our straight line here. For subfigure 2, I'm plotting our Fibonacci series, which you see here. And this is just to demonstrate that matplotlib is state-based, which is kind of slightly weird. So you can, like, basically it refers to the last figure that was added. It keeps it kind of like in memory, and you can say plot.plot on the last figure. And it's kind of like, and the last figure that I created here, or the last subplot I created here, was this one. And so that's why this dashed line, I specified a dashed line here with this k minus minus parameter. This is a style option. The dashed line appears down here. So this is how you would create a compound chart with multiple subfigures. There's also this subplots shortcut. And we can then use, like, this returns our figure and the axis, which is also what the subplots are sometimes called. And this returns a 2-dimensional array. And I can then refer to them by index. So I can say axis or subplot 0, 0 is the one on the top left, 0, 1 is the one on the top right, 1, 0 is the one on the bottom left, and so on. Or again, we can use like tuple unpacking as we've seen before. This is just the same thing. It's maybe a little bit more readable like this.
I have a quick question.
Sure.
In the last example where you did, in this one, is it possible to specify the figure size here if you wanted?
For the subplots or for the overall figure size?
I think for the overall figure size.
Yeah, you can specify the overall, like, you can do this here explicitly. So if I were to do, like, because it's kind of state-based, well, that's a good question, but that it probably should work. Let's try it. The answer is it's definitely possible. The question is whether I'm guessing the right syntax here. Immediately, no, I'm not. So I would have to look up the documentation for subplots. I'm sure there is a way to specify the figure size.
Okay, thank you.
Okay, so like we've done only line charts. We've done line charts on top of each other, line charts next to each other. But now let's look at a couple of different visualization techniques. So one thing that we'll talk a little bit more in detail about is which visualization technique is appropriate for which scenario. And what we'll look at here today is, like, we want to visualize correlations between 2 dimensions, numerical dimensions. And for that, we can use a scatter plot. If we want to visualize some raw data in a single dimension, we could use, for example, a vertical bar chart or a horizontal bar chart or a pie chart if you want to show a part of a whole relationship. And then we could also visualize distributions, which is often very useful if you want to explore a large data set. I'll talk more about distribution plots on Thursday, but basically you can either do box plots or histograms, or kind of my favorite is violin plots. And so this is kind of like a little bit more complicated code cell here, where you see all of these different charts. So here we have like a scatter plot. Here we have a vertical bar chart. Here we have a horizontal bar chart. Here we have a pie chart. And then at the bottom here, we have distribution charts. So we have box plots, and then we have a histogram, and then we have 2 different, slightly differently styled versions of violin plots. So yes, there, yeah. So here's the fixed size parameter. Thanks, Ike. Yeah, I was sure that there is something like that, but that's the way to explicitly specify a figure size. Yes. Great. So let's look at what I'm doing here. It's really like this. These are just all that. Nothing super interesting is happening here. I'm in my subfigure 0, 0. I'm putting my scatter plot with just some kind of like made up data. Then my bar chart, I'm like specifying the first array are the X positions, and the second is the value or the height of the bars, the value of the data or the height of the data. In my horizontal bar chart, I use the .bar h function. And similarly, like I'm specifying positions, and then I'm specifying the size or the data, and then I can also label them explicitly here. Like in this case, I've just done A, B, C, and D. Pie charts are like something that people really seem to like. I don't know. This is maybe like Excel in the 90s is what primed people on pie charts. Pie charts are pretty problematic in terms of how accurately they can represent data, but they're useful in certain limited contexts. And so here's how you do a pie chart in Matplotlib. You simply say pi, you give it the 3 values. It takes these to be part of a whole. You can specify your labels like this here. And then I am also kind of like limiting how like these percentages are automatically calculated behind the scenes, and it doesn't really make sense to show me like 3 numbers below like after the comma. So I'm just specifying I want to like at least at most see a single value after the comma. So yeah, that's how you create a pie chart. Box plots are kind of like they visualize like the mean of the distribution plus the interquartile range plus some 1.5 times the interquartile range, or what exactly the whiskers are. I always forget. And then additionally, they show the outliers. So they're kind of a succinct representation of a distribution. If you don't have a lot of space and want to use many of those, box plots might be quite cool, but you should also make sure that you have only that you don't have a bimodal distribution, because bimodal distributions are not really well represented by box plots. And so box plots is pretty simple. I'm just putting in these two, like the distributions that I create up here with random data. I can just put in an array of these arrays, and then I create the box plot out of it. The histogram is kind of like really interesting or a really useful visualization. A histogram, I'll talk more about how it's created. The big deal about histograms is how many bins I have. Matplotlib gives you an automatic guess, but you can also specify your bins if you would like to. So like, let's say if we do this here, bins is 20. We get a much more jagged histogram here. But you can frequently, like you should look at different bins if you really want to make sure your analysis, but you can often trust the default parameters here. And then violin plots are essentially like they show like a kernel density estimate. So it's kind of like a fancy version of a histogram. I'll talk more about how these violin plots are created on Thursday, but you can simply like just call .violin plot and then pass in an array of your for your distributions. I kind of like to see a violin plot also with the means. That kind of like gives you some interesting information. And I don't find these extremas that are default in Matplotlib all that useful. So I can just say, I don't want to see the extrema. I don't want to see a vertical bar here. And that's kind of like the chart you get. Okay, any questions about any of this so far? Great, so then let's move on. The other thing that we want to look at next is a heat map. And so I'll show one quickly. This is what I mean with a heat map. So I have like a 2-dimensional array here that has like a different values for each of the cell. And so just imagine, like, for example, you could do a heat map like this for, let's say, property values over Salt Lake City, like if you have a spatial data set, or anything where you have 2 dimensions, you can plot it as a heat map in some way, right? But this is also like useful. This is also how image data often comes in Python. So you have just two arrays, like a nested set of arrays that give you the pixel information, and then you can use more or less the same kind of like functions to show an image as you could use a heat map. And so a heat map, there's 2 ways of doing this, and they are kind of analogous, but they're slightly different in their purposes. So there's pcolor, which is really mostly for like the heat maps, and emshow is for images. This is like EIM here stands for image, of course. And they only really differ in their coordinate system. In images, like in photographs that we take, for example, we usually assume an origin at the top left of the image, whereas in data visualization, we usually assume an origin at the bottom left. And so that's the main difference between the 2 of them. And if we want to do like a heat map, an abstract heat map, we need to kind of specify a color map. And Matplotlib has many color maps baked in. You can also come up with your own color map, of course, but color maps, designing color maps is kind of a tricky business. And so I often recommend this tool here, which gives you like different kinds of color maps. So you can look at what is the type of your data? Is it sequential data? Is it diverging data? So do you have like a neutral middle point, or is it qualitative data? And then you can say, I have so and so many classes. And then you can also specify your color map. Is it supposed to be safe for colorblind users? Well, that's a problem for so many classes. So I have to kind of go down. Does it have to be photocopied, right? Photocopying is kind of like really tricky. So you won't find a lot of color scales that are photocopy safe, at least not in qualitative. And then you can export those numbers, but also many visualization tools, including Matplotlib. Like this is such a prominent tool nowadays, Color Brewer, that they just bake in these color scales. And so we'll be using some of these color scales. Here, and just like, you don't have to like read this. I'm just generating the data set here that we have, this nice kernel. And so like all I need to do is I need to say plt.pcolor, and then I put in my data set, my data set, and then I'm specifying the color map. So plt.colormap.blues. And then I also want to plot a legend. Like this is plt.colorbar, and then I have my my heat map here with my color bar on the right. And similarly, this is emshow, just to show you that this is in fact the same thing. It's just like, as I said, inverted in terms of the coordinate system, but in this case, it looks very much the same. And if I wanted to use like a Color Brewer color map with like a more fancy color scale, I could use pld.color map PUBUGN. And these are kind of like, you can see the names of them. PUOR is the name of this one here, and so on. Okay, so the thing is that you also want to do different styles sometimes, and we can do like a global style with like a command like this. And if we do that, I'm just rerunning this, and so now you see everything here looks more like ggplot from R. There's like a predefined style. But you could, of course, also create your own style if you like work for a company and they want to develop their own kind of like visual vocabulary. Then you could create a style and use that. But there's a couple of good default ones. Here's a style based on a Seaborn library that we'll be later using. Or if you want to go grayscale, you can also do that. So that was kind of like the raw Matplotlib, and now I want to talk a little bit about plotting with pandas, since we've already done some of this. Like some of this is just going to be a recap. I'm loading again our movies data set, and you've done this before. This is really just for completeness sake here. I can plot a line of my data set if I want to. some of the things that you might not have done as much are like the more advanced things that I'll be doing next here. I can plot a histogram, and that is super easy. I'm just doing dataframe.plot.hist. There is kind of like a legacy method. So if you see that somewhere, don't be surprised. But this is kind of like the way to do plot in pandas going forward. And I can also do like multiple multi-dimension on the same scale. So here I loaded this iris data set that we'll be using a couple of times. This is like 3 different iris flowers and their properties, like how for sepals and petals, how long and how wide they are basically. And so we will be using this, for example, in some classification tasks, so whether we can distinguish these species. And here I'm plotting actually all of the species together, but just those different values as separate histograms that are overlaid on top of each other. Pandas also supports kernel density estimates, which is basically what the violin plot is. So I can say .plot.kde, or I could do that with the iris data set. And so here, this is probably a better plot than this here, because here we have a ton of overlap, right? And this here is with the line chart, that's kind of much cleaner. We can do bar charts in directly with pandas, so we can do something like I'm subsetting the data set here because I don't want to create a bar chart with thousands of bars. And I am here just plotting for selected movies the actual title of the movie and their rating in the bar. So fairly simple. We can also create grouped bar charts. Here, you have to make sure that the values are on the same scale. So I'm creating a new data frame where I'm kind of putting in heart rates of people. I am giving, like, the index here is 3 names, Robin, Katie, and Chuck. And now I can see that Chuck had like the same heart rate in stage 1 and stage 2. Katie was lower in 1 than in 2, and so on. And I'm simply doing this by calling bar age here. And we can also create stacked bar charts, which doesn't make all that much sense for this particular data set, but you just have to put in the stacked parameter here. So like, as I said, it doesn't make sense to stack heart rates, but you can do it if you like. Something interesting is always the scatter plot, right? So like you might have created a scatter plot like this for your homework. So this is fairly easy. You simply say plot.scatter, then you specify what your 2 dimensions are, and that's it. But one thing that you might have noticed is that we have like a lot more movies in, let's say, around here in the 2000s. So we might be overplotting some points. And one way of addressing this problem would be adding some alpha value. And so I'm making this here only 40% opaque. And that means that if I have like these darker spots here, that tells me that there's multiple points on top of each other. Whereas here I can see that there's only probably only a single movie, or I could go down even further, could do 0.1. And then I would see, it's really like, this is kind of the most dense area in here. And again, just a simple parameter. I can do box plots with pandas, or I can create box plots for the data grouped by in their column. So here I'm creating like a box plot for every single year for all the ratings to give me kind of like an aggregate view of how did ratings develop over the years. And we can see that they're fairly narrow in the past, but then as we get into more recent years, we have like a spread of these ratings. One thing that we very frequently will do is we will look at higher dimensional data sets. And visualizing higher dimensional data is problematic. One useful technique is what's called the scatterplot matrix. And the scatterplot matrix is just a series of scatter plots mostly. So here I'm plotting year, length, and rating on both the X and the Y axis. And this scatter plot here just visualizes year versus rating. This here visualizes rating versus length. And then in the diagonal, I'm kind of like visualizing rating versus rating, but that doesn't make sense as a scatter plot. And so I'm using a histogram in here. And so this is like a pretty succinct representation of this whole data set. And so if I want to explore a data set, then I often start out with a scatter plot matrix. And so that's something that you could do, for example, in your homework when you look at the real estate data. Again, I'm using some alpha values here because I have a lot of overplotting. But yeah, that's an efficient way of doing it. And I can also, like, if you prefer your kernel density estimates over your histograms, you can do that just as well. And then sometimes, especially when we like learn about classification, we will have some kind of like predefined classes. So here, this is the example of this iris data set where we have the 3 different species like Setosa, Virginica, and versicolor, and I'm assigning them a different color value each so that I can start looking at, hey, are these classes nicely separated? And so what you can see here is that the red class is actually fairly nicely separated, right? So I can probably find like a classifier just in 2 dimensions to separate those from the rest of them. But the violet and the blue ones, they tend to be a little bit more interwoven. So it might be a little bit harder to separate them out. Okay, so yeah, these kinds of charts are super useful to explore data sets, to see like what's going on. And they're really easy to create if you have things already in your in a pandas data frame. So I definitely recommend that this is always your kind of like your first stop. And now I want to go into some a little bit more complex visualizations, but first we'll take our 5-minute break for today. So I'll be back at 1:05. Okay, so let's take a look at Seaborn. Seaborn is a great library if you want to do a chart that that you can easily see that is available in Seaborn. So there's like this nice example gallery of some advanced charts, for example, like a heat map, a cluster map with like a dendrogram and so on. Things like that are actually pretty tricky to create in Matplotlib, but Seaborn allows you to like basically either look up the examples here, or it's maybe just like a simple single call. And so I like to use Seaborn when I do some like data analysis, but don't need any interactivity. That's kind of like my library of choice nowadays. And so I'm importing Seaborn as SNS as is customary. And then I'm loading a data set here of tips in a restaurant. Like we have dimensions such as the total bill, how much tip was given, like the sex of the person, whether they're a smoker, the day, the time, is it dinner or lunch, and the size of the party. And you can already see this is a little bit of a data set by like specifying smoker here. But interestingly, so here we can create, for example, like what Seaborn calls a relationship plot, which I call a scatter plot, and I think everybody else does. But it's called rel plot in Seaborn. You can say like the data is the tips, my x-axis is supposed to be the total bill, my y-axis is the tip. Then I'm setting a hue to smoker, and then I'm setting the size to the size of the party. And what we get is this like really nice scatter plot that has all the legends already in there, right? So this is like a very convenient way of creating that scatter plot. And now we can try to analyze, is there any relationship between kind of like, do smokers tip more, or do does this size of the party affect tipping, and so on. And then we can do things like faceting plots, which is always super useful, like faceting plots by a categorical column. And so here I'm faceting the plot by the day. So I can look at, well, is it Thursday, Friday, Saturday, or Sunday? And I have now 4 different plots. And this is called like a principle that's called small multiples. So I have like, if I have an additional categorical variable that I want to show here, if I were to encode, let's say, the day in color, it might be kind of tricky to spot the relationships. And so instead, I'm simply faceting it by specifying the color column here, or I could also facet by time, which is kind of like, is it dinner or lunch? And we can see that, well, dinner overall seems to have some higher total bills, not surprisingly. In this case, I've also used different symbols for is it a smoker or yes or no, and I'm used redundant encoding, both color and the symbol, to encode whether it's a smoker or not. Very useful are all kinds of categorical plots. So these strip plots is something, if you look at a lot of data, they can be quite interesting, because you're looking at the raw data instead of the, like if you look at the histogram or kernel density estimate, they hide some information, right? Looking at the raw data, especially if it's not too much, can be quite useful. So like this is called like a cat plot with a kind strip. And then you just specify the rest of it here. Or the bee swarm plot is something that you might have seen before. It's the same command. It just, you say kind swarm, and the bee swarm plot makes sure that there's no overlap. So it kind of like spaces it out so that no 2 points overlap. And so you could conceivably say, well, I might miss some points in here. Here you can see that this is all spread out, needs a little bit more space, but you're making sure that you're seeing every single point. You can, of course, also create violin plots in Seaborn. So here I'm creating a violin plot that is faceted by smoker yes or no. So I have the smoker yes on the left and the smoker no on the right. And now I can kind of like facet this further by the weekdays. And so I have like a very succinct and efficient representation of like a pretty complex like faceting of this data set already. And then we can use what they call like joint plots to combine multiple plots with each other. So here I've loaded a data set of penguins. We have 3 different species, Adeline, Chinstrap, and Gentoo penguins. And I'm plotting flipper length versus bill length in this case, and I'm color coding the species. And the scatter plot here, we've seen that before, but here it's also nicely juxtaposed with kernel density estimates for the flipper length in this case here, and for the bill length in this case here. So that kind of gives me 2 perspectives or multiple perspectives on the data set, which can be useful. And then finally, I can do like a scatter plot matrix, or what they're called pair plots in Seaborn, just as I can do with pandas. And this takes a second, but then like this is the output here. And so again, a pretty nice plot. We have basically like the only thing we've done here is setting the hue to species, and everything else happened by itself. And so that's a very efficient way of specifying a scatter plot matrix. Okay, so the point here, like I don't really want to, these are just library functions, right? You can look them up, but I wanted to give you kind of an idea of what Seaborn is good at, so that you can pick the right tool for the job. And so for the rest of today, I want to talk about a completely different approach here. This is kind of like Altair. And Altair is a modern plotting library based on Vega and Vega Lite. Vega and Vega Lite are kind of like JSON-based declarative visualization libraries that you can that are fully native on the web. I'm not going to go into the details about this, but essentially Altair is a Python wrapper to these. And if you haven't already, you will have to install it because that's not part of your standard package. But if you have already done this, you can import this. Altair works really well together with pandas. So that's a big plus. And I'm gonna, like, again, use our movies data set for these examples here. So the principle of Altair is that I have kind of marks that represent like an item, basically a row in a table. And then I can specify how should that mark be rendered. This is the most basic Altair chart. What I'm taking here is saying altair.chart. I give it the data set, and then I'm saying, give me a mark point, but I'm not specifying at all how it's supposed to be rendered. And notice that like the big difference here is there's no scatterplot matrix function like in Seaborn here. This is like a single line, right? In Altair, this would be much more complicated. But of course, it also gives you flexibility. So if you want to do something more custom, and especially something interactive, then Altair is the right tool. So here I've created a chart where every single item is visualized as a dot, but I haven't specified the position or anything like it. So this just shows all these dots on top of each other. So that's not particularly useful. And so what I want to instead is I want to say, Altair chart, the data set mark point. So I want to use points. And then I want to encode the X value of the points to my average rating dimension. And so what this will give me is essentially like a single dimensional visualization of these like points spaced out. And I can already see that this is similar to what we showed earlier with the strip plot. So the idea really is like you specify everything on your own here. There's a couple of different marks that are available. So you could use a point, you could use a circle, you could use a square, a line, a bar, an area, or a tick. You can also get this list with autocomplete. But let's look at this particular chart up there that might be actually better served in with tick chart instead of like a point chart here. Or yeah, this was a mark point. So same approach. The only difference here is that I've said mark tick. So the interesting part, like here, I have encoded the X position, right? And when we encode visualizations, we have like a limited vocabulary of like what we can use to encode. And those are either X or Y values, the color, the opacity, the shape of the mark, the size of the mark, And then we have two special ones here. These are row and column. This is for grids of faceted plots, which we'll take a look at later. But these are the basic encodings that we have. And so, for example, I could do something like, I want my Y position to be my average rating, now Y instead of X. And I want to size the points based on how frequently the movie was watched. And now I create something like this. And behind the scenes, Altair also creates the legend for us, and it does some other smart stuff in addition to that. So one of the central ideas of Altair is that the library will try to choose good defaults for your data type. And there's a couple of different data types that are supported by Altair. Like we've seen those before: quantitative, nominal, ordinal, and temporal. And when you specify data as a pandas frames, these types are automatically determined by Altair, right? So if you have an integer or like let's say a floating point number, it will be automatically specified as quantitative, but you can override it if you want to. So let's look at how we would create a scatter plot in Altair. We could do something like, it's not particularly surprising. I'm simply saying X is this, Y is this. And now I have my scatter plot here. One rule in visualization is that charts, or some people say that charts should usually start at a 0 axis, or the axis should start at 0. But of course, this doesn't make a ton of sense here, right? Because the 0 point in years is more or less arbitrary, and I'm squishing everything up here. But by default, Altair gives us kind of like this 0 based axis scaling. And so I have to change my axis scaling by explicitly saying alt scale 0 is false. And so if I do that for X and Y, I get a scatter plot. I get a scatter plot that looks a lot like what we had before. And we can replace this point mark with a circle, and it will look like this. And this looks a lot like the charts we've drawn before. And now we can use kind of like the color channel to specify the genre. And I'm using here like a subsetted movie. I'm just picking 3 colors because you don't want to pick too many colors. I'm looking at children's movies, horror movies, and documentaries. And if I do that, I get a scatter plot like this. So we can see maybe that horror movies tend to have pretty poor ratings on average. It looks like somewhere the average is somewhere around here. And documentaries tend to have pretty good ratings, but there's not a lot of old documentaries. And children's movies seem to be kind of a little bit more evenly spread out. So they have a more even distributions of their ratings. We can also color by a continuous variable. So for example, we can color by watches. And so we can look at, is there a correlation between release date, average rating, and how frequently they were watched? And we can see that there are some movies that are fairly highly rated and were recently released that are very frequently watched. So notice that I didn't specify a color map here. I didn't say this is I want a blue, orange, red color map, or I want to have a continuous blue color map. Altair just inferred this from your data type. In this one case, it was continuous. In this case here, it was categorical. And so it inferred this, and it also created a legend for you. Okay, so then we can create more complex charts using these kinds of functions. And so here, for example, we can put in a count function for our y-axis. And you can already see that I'm actually specifying a function as a parameter. So you can see that something is happening behind the scenes that translates this into another language and applies that function. And so if I do that, this is the way to create a histogram. So I'm saying my x is x and average rating, and I'm binning it, and my y here is at the count. So this is kind of not particularly, let's say, it's much more complicated to visualize a histogram like this, right? Than if I just call hist on my data frame. But I'll show you why this is still a good idea a little bit later. we can control like bins, for example. I can say max bins is 5. So like I can in the other charting libraries, I have these kinds of parameters available. And the data will be automatically grouped within each bin if we, for example, apply another encoding. So for example, color. So here the difference is I am saying color is genre. And that might be like a chart that's actually already tricky to create with matplotlib directly. But here, just because this is kind of like I'm just declaring use color genre, and it automatically creates this nice bin chart where I can get a sense of like what is the distribution of these values. And we see the same effect that I mentioned before. Horror movies tend to be lowly rated, documentaries tend to be highly rated. We can also like facet a chart by using the column here. And this is similar to what I showed before for Seaborn. Now I have 3 different histograms for the children's, documentary, and horror movies, just by saying I want to have the column mapping to that particular channel. Here is an example of how I can create a line chart. This is simply, I'm saying X is my release date, Y, and I'm creating here an like a mean of the average rating. So I'm creating kind of like a binning here. And then I'm setting the scale to not start at 0 as we had before. So this is similar to what we've seen before. This looks a little bit different from the original data set because I'm looking at a different subset of the data set. Okay, so now it gets a little bit more complicated. So what we want to do is we now want to create compound charts. So let's suppose we want to create like a histogram and a scatter plot. The histogram of genres, like how many we have, and a scatter plot of released versus average rating. So I'm specifying both of those charts here, like we've seen those separately, and then I can create this compound chart using this vconcat function and passing in those 2 visualizations. So that's kind of like the common or an obvious way to do it. There is something that's called operator overloading, and so I can actually specify this with this weird syntax. So you might not have seen this before. Yes, there's a hconcat. I'll talk about it in just a second. But let me first talk about this particular syntax here. So this is actually the operator here. Does anybody know what that operator does in standard Python? It's a binary AND operator. So it actually takes the AND operation of the binary representation of a number. But it turns out that there is something that's called operator overloading. So I can tell Python for specific objects, take this here and like take this operator. But what I want you to do, if you see those 2 objects with this operator, I want you to call this function. And that's kind of like slightly weird, but it's super convenient, right? Because this is like a very succinct syntax. I'm saying histogram and scatter, and it gives me this vertical concat. Similarly, I have hconcat, which is mapped to the pipe operator here. So I can say scatter or hist or pipe hist, and then I have those 2 side by side. And then finally, there is the overlay operator. I can say layer, or I can use the plus operator. And so I'm creating here a chart, like a histogram of for every year. And then I'm like plotting this at the same, like overplotting it with the scatter plot that we had before, where we have our average rating versus release date. And in this case, I'm actually using 2 different y-axis. And so I have the count of records for the histogram and the average rating for the like individual data points, which isn't something that like, yeah, this I think chart is fine, but having two different axes is sometimes a little bit tricky, so be careful about that. But the interesting piece here is that I'm using this plus operator to indicate that I want to have a layer chart. So these two on top of each other. And then I also want to say I want them to be on an independent scale. So if I didn't do this, they would be on the same scale. And then that would look not that great. Okay.
Is that operator overloaded by Altair? Did you overload it?
No, that operators are overloaded by Altair. But you can also operate your own. You can also overlay your own operators if you want to. But I'm basically saying this because if you look at the examples in Altair, they will all use this syntax. And when I saw it for the first time, I just didn't know what was going on, and I actually didn't even know that Python supports operator overloading, which is something I know from C and C++, but I didn't know from Python. So, but it's pretty cool once you get used to it. Okay, so now for the really cool part, we can do interaction. And what I'm like doing here is I'm creating just like a simple chart as we had before, and I'm making it interactive. And now I can zoom in and I can pan. That's kind of like the standard interactivity. So you can kind of resolve these ambiguities a little bit if you want to. And that now, of course, works because this is no longer just a simple figure, but I'm actually creating like an SVG visualization in the background that is dynamically rendered in my browser. And so zooming and panning is nice, but of course, we want to do something more sophisticated. We want to use selections. So if we really want to understand complex multidimensional data, interaction is really important. And this is really where Altair is better than any of the other libraries. There's some ways of doing interaction in Matplotlib, but it's super sophisticated in Altair. So if we we want to specify if we want to select something. So I'm saying here Altair selection interval. So I want to select intervals. And then I am saying, this is just my visualization. And then I'm saying add selection. Or I can also add property with selection interval, or I can say add selection interval. And what I get then is like a rectangular brush that I can draw here. I haven't said what this is supposed to be doing. So it's just a brush, right? So it's not doing anything, but this is how I create the brush. When I want to react to the brush in some way, I can use the Altair condition function here. So I can say the color, I want this to be conditional on my interval brush. And if it's not in the brush, I want to show it in light gray. And so what I get now is a brush where only the points that are under the brush are color highlighted. So this is getting us somewhere. But of course, this really gets most interesting if I can use this to look at another chart, right? To look at the subset in another chart. And so the selection API automatically applies to all compound charts as long as they have the same selection applied. And so I'm setting my interval selection here again. And then I am creating here like a base chart. And then I'm creating two versions of this chart. One encodes the average rate, like both of them encode the release date on the x-axis and have my color conditional on the selection. It's genre colored, but it's also conditional on the selection. And then I am taking this base chart and I'm creating two versions of it, one with the average rating, one with the watching. I'm plotting them side by side. And so I have these two charts, and now I can select in one chart and see what the corresponding items are in the other chart. And so this is kind of like a neat way of looking at kind of correlations between those two different charts. I can look at the high ones, like the highly rated, the recently released and highly rated ones. Where are they in terms of watches? And I can see that, well, they're kind of all over the place, but some of the most watched ones are definitely in here. And then we can combine this layering and selection API to do some fairly complicated interactions. And so what I'm doing here is I am creating both like this color filter, but I'm also showing you like a chart that dynamically visualizes a histogram only for the data that I have selected here. So I can, like in either of these charts, I can select, and my chart here at the bottom dynamically updates. And so how do I do this? Fairly simple, actually. I am simply saying I want to have a transform filter that listens to that selection. So here I'm specifying my histogram. This uses the same code as before. And then I'm just saying, filter it to the selection that I set up there before. And then I am creating like one compound chart with the scatter plots, average rating, and next to it, the watches. And then I'm creating like a vertical compound chart of scatter plot and histogram. And then I have the result here. And then finally, we can, of course, this doesn't have to be like that. I can also create, like, I can say that my scatter plot is supposed to be filtered. And so now I can kind of create anything that I want. Like this is like a this is not just a library, right? This is like a little programming language. And so I can create as complex as dependencies and interactions as I would like to do.
Just a quick question. So do we have to define like the interval? Do we have to define that in the like data frame or in the plot, or can we define it separately and reference it?
So I am just saying like I want an interval selection, and the interval here is defined through me clicking and dragging on the browser here. Does that answer your question?
Yeah, kind of. Like, so the interval selection is defined by like the part you're interacting with on the browser, but
yep,
like if I wanted to like make it make a class for an interval selection to apply it to different kind of plots, I could do that, like to reference it differently as opposed to just write in on the.
So, okay, I'm not completely sure. I'll try to answer two different versions of your questions that I think that you're saying. Okay. If I want like this selection here that applies to all of the plots simultaneously, right? So if I, like, as you see down here, like I can select in either this chart or in this chart just based on one single selection, and it's propagated to all of the different plots. So an interesting question would be, can I actually extract the data out of this, right? Can I use this as a filter? And the answer to that is yes, but I don't have an example here right now. So, but yeah, it would be interesting to kind of like get the items that are in that particular selection out. Maybe you could do something like, I want to filter out my data manually, like in an interactive system, right? And then process that further in Python. Is that what you mean?
Yeah, that helps. Thank you.
Cool. And then I don't want to go into the details here, but I just wanted to show that you can also do geospatial visualization with Altair, which is not possible with any of the other libraries. Geospatial visualization here that works based on kind of like importing TopOJSON. So this is a choropleth map. This is not backed by Google Maps or anything like that, but I'm actually like retrieving this from like, this is like explicitly drawing the counties here, and then I can map something to it. I don't want to go into the details. This goes beyond it, but if you're interested in your project to visualize some geospatial data, you could look at this example, and there's other maps. So for example, here is like locations of airports, or you could have like a repeated color pleth map, or look at income by state. To do this, you have to usually have like a JSON, like a TopOJSON data set, and this is kind of like what's specified here. Those are fairly easy to get for like US states, US counties, and so on, but that might not be all that easy to get like a meaningful for your homework. The map solution might not be like this might not be the right way. You might want to use a different API where you have like a street map below it. So yeah, explore that if you would like. For the last 10 minutes, I have prepared a little exercise for like you're just like trying to something out with Altair. You should create a scatter plot with dimensions of your choosing for the movies data set that you can brush. And like instead of the basic histogram that I showed before, you should just use this stacked histogram. And then you can submit this into one of your Dropboxes if you still have one available. So I'll open up the breakout rooms in just a minute, but I'll take questions first. Okay, doesn't seem like there's a question, so I'll open up the breakout rooms. Thanks, everyone.